Now, based on the fact that the trig functions are defined on the unit circle, will the graphs of the trigonometric functions have any other properties that might be useful? So, let's look at cosine. Okay. Cosine is defined to be the x-coordinate on the unit circle. Okay. So, if I have an angle, theta, it will have coordinates x and y. If I look at negative theta, which is the same angle but turned the other direction, the coordinates of this point will be x, comma, negative y. Notice they have the same x-coordinate. This means that the cosine of negative theta is just equal to the cosine of theta. Okay? If you remember, this means that cosine is an even function. It also means that its graph will be symmetric across the y-axis. Now, let's look at sine. Sine is the y-coordinate, and from this calculation we've already done, we see that the sine of negative theta will be negative the sine of theta, because the sine of negative theta is negative y, which is negative the sine of theta. This means that sine is an odd function, and also that the graph is symmetric about the origin. From these two, we get a whole class of identities called the reduction identities. So, sine of negative theta is negative sine of theta. Cosine of negative theta is cosine of theta. Tangent of negative theta, because it is sine over cosine, turns into negative tangent of theta. And then the reciprocal ones, cosecant of negative theta is negative cosecant of theta. Secant of negative theta is secant of theta. And cotangent of negative theta is negative cotangent of theta. So all of them you can pull the negative sign out except for cosine and secant, in which you can ignore negative signs. Now, we're going to start looking at trigonometric equations next. And so we're going to want several more classes of trigonometric identities. So the most important trigonometric identities come from the most important theorem in this class. And that is the Pythagorean Theorem. Okay, so draw a new circle. If you pick a point, we have 1, x, y. And if it's not on the unit circle, you can have the radius be anything you want. We're going to do the general case here. Okay. We know that the sine of theta is y over r, and the cosine of theta is x over r, using SOHCAHTOA. Now, the Pythagorean theorem says that x squared plus y squared equals r squared, because this is a right triangle. I'm going to manipulate this a little bit to turn it into the Pythagorean theorem identities. First, I'm going to divide everything by r squared to get a 1 on one side. Then I'm going to rewrite this by taking the square out of the parentheses. And then I notice that this is cosine squared of theta plus sine squared of theta equals 1. Okay. So this gives us our first of the 3 Pythagorean identities, which is usually written as sine squared theta plus cosine squared theta equals 1. Now, what can happen is if you take this, okay, and you divide the entire thing through by cosine squared, okay, well, sine squared divided by cosine squared is tangent squared. Cosine squared divided by cosine squared is 1, and 1 divided by cosine squared is secant squared. So I get my second Pythagorean identity. If instead we take the original and divide through by sine squared of theta, we get cosine squared divided by sine squared is cotangent squared. Sine squared divided by sine squared is 1, and 1 divided by sine squared is cosecant squared. So we get our third of the Pythagorean identities. And together, these 3 identities form the most useful trigonometric identities.